Hello everybody. In continuation of my previous discussions on the recent advances in high voltage engineering, today I want to speak about the applications, R&D and future outlooks. And especially I will discuss about the next decade of high voltage engineering. High voltage engineering is rapidly evolving with the new applications worldwide. In the last 10 years, deployment of renewable energy has driven innovation. On the other hand, offshore wind, solar, and BESS clusters all depend on the advanced high voltage systems. R&D efforts have accelerated in the cable, converters, and protection systems. Then in this talk, I will try to highlight the recent applications, research, and the road ahead. First of all, let's talk about this important issue, why applications and R&D matter. The practical applications show how the technology moves from the laboratory to the reality. The R&D investment guide the next generation of high voltage solutions. It must be noted that without deployment, innovations remain theoretical and unused. Without R&D, reliability and sustainability targets cannot be met. Then applications and research are inseparable in the shaping high voltage progress. But high offshore wind and renewable hubs are very much important in this field since offshore wind farms have grown rapidly in Europe, China, and in the US since 2015 during last 10 years. These projects rely on HVDC export systems up to 525 kV. Multi-terminal DC or MTDC hubs are being piloted in the North Sea as well. Advances in cable and converters make these systems possible. And I have to note that offshore grids are the backbone of the energy transition. About the solar PV, BSS, and hybrid projects, I have to tell you that large solar PV plants above 500 megawatts are now common globally. BESS has expanded massively in the last 10 years, especially in Australia and in the US. Hybrid projects combine PV, wind, and storage for the stable power delivery. On the other hand, converters with the grid forming control integrate these diverse resources. Such projects have moved from the pilot to the mainstream deployment, especially in US and Australia. In the field of application, they have too much of applications in mining, industry, and hydrogen usage and hydrogen production also. Electrification of mining operations has accelerated in the past decade. Industrial parks and data centers increasingly require HV high voltage connections. Green hydrogen clusters depend on large renewable inputs via HVDC. Converters and switch gears enable enabling the integration at scale. Then I have to tell you that these applications show how HV supports decarbonization beyond the power. Another important issue is related to integration with the storage and power electronics. BESS is connected at HV levels. They provide a fast frequency and high voltage support. Wide bandgap semiconductors have advanced converter efficiency. FACTS devices and HVDC links are co-optimized for grid stability. Hybrid AC to DC networks are now being tested globally. Then I have to mention that these advances highlight the blending of storage and power electronics. But what about the recent R&D frontiers? Advanced dielectrics with nanofillers improve the cable insulation performance. Hybrid and solid-state DC breakers are being refined for the commercial rollout. Online space charge sensing is moving from the research to the field application. This is very much important in the field of high voltage DC and dielectric materials which are using in this field, since the space charge transport is very much important in these devices. AI-driven diagnostics are creating synthetic data libraries for the training models. R&D is closing the gap between the reliability needs and renewable growth. But it is interesting to talk about some case studies from the last 10 years. China ultra-long HVDC lines now exceed 3,000 kilometers in operation. Europe has deployed 525 kV subsea cables for the offshore wind integration. Utilities in Germany and Switzerland use SF6 frig switchgears at transmission voltages. Australia has piloted a large BSS integrated with HV grids since 2018. Then, these real-world cases prove that advances are practical and scalable. This is a good news. Future outlook. But what about the future? The next decade will see MTDC, multi-terminal DC networks, moving from the pilots to full deployment. Global rollout of SF6 ferry switchgear will become standard practice. AI will transform diagnostics, control, and predictive maintenance. On the other hand, hydrogen production and electrification of heavy industries will expand the high voltage applications. Well, then we can say that by 2035, HV engineering will define the backbone of a net zero energy systems. Energy system. In conclusion, I would like to tell you that in the last 10 years, HV applications and R&D have advanced significantly. Renewables, storage, and industrial electrifications are reshaping HV demand. Key advances in converters, insulations, and protections are enabling this shift. Future outlook points to MTDC networks, AI-driven diagnostics, and green hydrogen. And finally, we have to say that high voltage engineering will remain the central to the clean energy transition. Thank you for your attention.